So here we go, vectors. All right, so first of all, hopefully you remember from last year that a vector is a quantity that includes both size and direction, right? So we refer to the size by using the word magnitude, okay? And then obviously the direction is the direction that the vector points in. All right, now last chapter we actually dealt with vectors, even though I think I probably didn't use the word at all, right? So velocity is a vector, which means it includes direction. How did we indicate the direction when we talked about velocity? Sure, we got here. Using positives and negatives, right? So up until now, all of the motion that we've looked at has been one dimension, right? So if you imagine a number line and you're traveling along that number line, there are only two possible directions you can move, even though it's one-dimensional motion, right? You can either go forwards or backwards, you know? And so because there are only two directions you go, we can keep track of signs, or keep track of those directions conveniently by associating positive with one direction and negative with the other. Cool? So the question becomes, what happens if we're not limited to just one dimension, right? Like what if instead of being limited to the x-axis, what if we can move anywhere in the xy coordinate system, right? And weirdly, that opens up an infinite number of directions you can go, right? Right? Because you can go forwards, and up a little bit, forwards and up a little bit more, right? There's like an infinite number of directions you can go. Okay? Quantities that are vectors, and again, a lot of this is review, hopefully. Quantities that are vectors, position, right? Your location in space is a vector as measured from the origin, okay? Velocity, direction is important. Acceleration, direction is important, okay? I think all this is review. Scalars. So scalar would be a quantity that doesn't have direction. Okay. Time is a scalar. Temperature, you wouldn't say it's 20 degrees down, right? That doesn't make sense. Energy and mass are scalars. Okay. They don't have directions associated with them. Okay. So scalars are what you've been dealing with your whole life, right? Like when you first started learning how to count, you were counting scalars. And so all of the math that you've learned through math has been in regards to scalars, all right? Vectors, to do math on a vector, you need to use vector mathematics. And so the rules are slightly different when you talk about doing math with vectors, okay? So basically today, we're going to talk about components of vectors and how to add and subtract them real quick. Yeah.
So I don't mean to be like snobby, but
No.
I was just wondering, I guess.
How much do these vectors earn?
No. So for energy, wouldn't it kind of have a vector from the perspective of the system it's in, almost like heat flowing into a.
Oh, I gotcha. No. So what you're talking about there is change. Mm-hmm. So the amount of energy has a quantity, right? Like 10 joules or 40 joules or whatever. And then the energy can either increase or decrease. But again, you're still just measuring. I know what you're saying. You're thinking in or out. Technically, I guess you could define any change as a vector, right? Something like that. No, I still think it's, sorry. No, I'm just processing. I'm just debating. I know what you're saying because you're thinking into or out of the system, right? But suppose this is my system and I've got energy flowing into it. Well, is it flowing from this way or this way or this way? It doesn't necessarily come from a place, The reason I'm hesitating is because the change can be positive or negative. But in that instance, the negative doesn't truly represent a direction in the sense north, south, east, west, up, down, left, right. You know what I mean?
Yeah. Linearly.
Yeah. So, I don't know. Does that answer your question?
Yeah.
Okay. All right. Are we all good with difference between vectors and scalars? Okay, cool. All right. So the simplest example that we can talk about for a vector is a displacement vector. Okay. Up until now, it's just been, either you go forwards 4 meters or, hey, Miss Payton, how are you?
Charlotte here.
Oh, hi. She's right here.
All the way in the door.
Yeah, I know. I'm sorry. Okay. So she's here.
I know. Thank you so much.
Yeah, I'm sorry.
I'll put this in the thing.
Okay, thank you. Are you going to just mark her present then?
Sorry?
Are you going to just mark her present then?
Yeah.
Thank you very much.
I'll spend those here.
Okay, thanks. Why are you such a burden? All right. Okay, so remember, you guys, displacement is the length of the straight line from an object's starting position to ending position. Okay? So, you know, if I walk from here to here, regardless of how I get there, my displacement is that little arrow right there. Cool? Let's see, what else do we need to say about this? I don't know, I guess that's it. I mean, this should all be a review for you guys, right? Okay, so here's one of the skills that you guys absolutely need to make sure that you're comfortable with. If I give you a vector, you need to be able to resolve it into components. All right, it's basically trig. Okay, so in this example, we've got Roy throws a ball at 40 meters a second the terminology we used last year was either above the horizontal or below the horizontal, right? APH was above the horizontal, PTH was below the horizontal. Okay, so in this example, here's the ball, it's being thrown. So we usually write the magnitude of the vector above it. And then we somehow need to measure this angle, right? So the idea is horizontal. And I remember, I think it was on the test that some of you guys, that we realized that some of you were confused about what above the horizontal meant. So the idea is draw a horizontal line at your sort of, at your origin. Draw a horizontal line at your origin, and then identify the 30 degrees. There it is. Everybody cool with that? With what I mean when I say either above or below the horizontal?
Yep.
Cool. All right. So here's my V. All right. And then we need to be able to find our horizontal component and our vertical component. All right. Notice, and it says it down here, in doing this, when I draw those components, you have to make sure that the arrowheads on your components are head and tail. Okay? I could have, if I had wanted to, I could have drawn my components this way. What's the only problem with doing that? Yeah, the angle's in the wrong spot, right? My angle's now not in my triangle anymore, right? Okay, so then you just go, oh, well, but if this is 30, then this is 60 degrees, right? Cool? So please make sure you're careful in identifying where the angle is, all right? Last year, 90% of the time, our angles were off of the horizontal, all right? But it is not unusual to see problems worded where it'll say a ladder leans against a wall, forming a 30-degree angle with the vertical, okay? So just make sure you're cognizant of where those angles are. All right, so I guess let's take a quick second and do the math real fast here, right? So our Vx, I'm going to kind of plow through the trig here. So our Vx here would be 40 times, would I use cosine or sine of 30? Cosine, right? Because it's the adjacent side. Okay, and that gives you a number that I don't know off the top of my head, but I do have a calculator. What is it? Well, but I want a decimal because it's science, not math. 40 times the cosine of 30, so you get 34.6. All right. And then our vertical component, we're going to use sine, and that one's 20. All right, everybody good with this? This is all review, yes? I probably shouldn't even be going over all this. Are we good? Yeah,
I just didn't know, like, if you guys are in BC, your calculator is always going to be radians, or whatever. Switch it, otherwise.
yeah.
Nice. Thank you so much.
Thanks, Evan.
All
Thanks,
right.
Evan.
No, you're totally right. And there were a couple instances last year where students took their whole test, and at the end they're like, oh, radians. So don't be that person. All right, sines. So the advantage to talking in terms of components, you guys, is now, if I know that Vx is 34.6 meters a second, because I've told you that it's the x component, i.e. the horizontal component, now I can use positive or negative to keep track of direction, right? So here we're going to make this positive because we've thrown it forwards. And my Vy is positive because it was upward, right? Make sense? Oh, thank you. Okay, all right, so there are two ways that we can write out a vector now, all right? So one way to do it is by using, is this the highlighter? Yes. To use magnitude direction notation, which is this. Okay? Now, another way that we can write out vectors, this we did not do last year. Another way that you can write out a vector is to write it in what's called unit vector notation. All right? And basically what it is like in geometry, you learn to write the coordinates of a point by writing the x-coordinate and the y-coordinate in parentheses, right? Okay, it's basically the same thing. We just, instead of using parentheses and a comma, we use slightly different notation, all right? So let me show you what that looks like. All right, so. Okay, so to write it in unit vector notation. Now in math class, do I even want to go there? I don't. All right, so here's how you write it in unit vector notation. You write the x-coordinate, so for us it's 34.6, and then you put a little I with a hat on it. I'll explain what that is in just a second. So that the I indicates, hey, this is the x-coordinate, plus, and then you write your y-coordinate, 20, and you put a little J with a hat on it, and then just put your units. And so you don't even use parentheses, all right? So this would be equivalent to, in your math class, you may have learned to write it this way. Have you guys seen that in math class or no?
Probably, but I don't remember.
Okay, it's basically the same thing. All right. This is what's used in the book, and oh, that was neat. Do it this way, because that's the way it's usually done by physicists. Okay, so is everybody good with this?
Yes.
All right, so here it is, unit vector notation. So let's talk about what the I and J are real quick. I don't want to go into a ton of detail on it, but so I in mathematics, this I with a hat over it, so the little hat is a vector hat, okay? And it's telling you that, or it's defined kind of like pi is a universal constant, right? I is a universal constant vector, and it is a vector of magnitude 1 that points 1 unit in the x direction. So this means 34.6 times that. So this right here represents this x component, right? Because it's 34.6 times 1 unit long in the positive direction. Teddy's about to ask a really awesome question. Yep, if it's 1, you just write I. Exactly. All right, good. All right, and similarly, what do you think the J means? It's a unit vector that points 1 unit in the y direction. Okay? And then K is the z direction, but we won't get into that. Cool? All right? All right, so weird notation, easy concept. Here's my x value, here's my y value. And you can remember ij, xy, right? Alphabetical order, easy peasy. Cool? Questions? All right. Oh, I will also tell you, speaking of the hats, when I write up my answers and when I write up my problems, it is a pain in the ass to get Microsoft Word or Google Docs to type an I with a hat over it, so I don't put my hats on it. Deal with it, okay? Sorry. That'd be great.
Just like little vector heads.
You have to remember the AP test.
Alright, yeah.
All right. Okay, so this page basically explains what I just told you guys. All right. This thing about the right-handed coordinate system I threw in there, we'll talk about it more later on. When we get to torque, we'll have to talk a little bit about the right-hand rule.
Oh, I remember that.
All right. And eventually, assuming you guys take more physics, when you get to E and M, the left-hand and right-hand rules, particularly the right-hand rule, are going to be your best friend. Because it gives you, I see some of you guys doing the thing. So the AP students last year taught me the right-hand rule differently than the way that I learned it when I was in school, but one of them involves giving people the middle finger. So that's always fun, right? Okay.
If you give personal
Oh!
Why? That's a double whammy.
Cool. So anyway, there you go. I like that. I like that way. I never learned it that way. All right. So I think we're good. All right. Questions about the unit vector notation thing? Okay, cool. All right. So I think I already commented on this. The whole advantage of splitting things up into components is that then you're dealing with vectors that are in one dimension, right? So technically speaking, if you're being really, really fussy about it, your AX and your AY, your components are scalars that you then multiply by a vector to give you a new vector. But, yeah, exactly. Who cares, right? Right, exactly. And that's what the little I does, is it says, hey, this thing's a vector that points that way. So, cool. And obviously you use negative signs just the same as usual. You know, if your Y component points down, then you're going to have minus, you know, AY times J or whatever. Okay, cool. I've really put in more information in here than we need, but there you go. All right. So adding vectors. So remember, when you add vectors, again, you got to place the vectors head to tail, right? Okay. So graphically, it would look like this, and this is sort of what the little drawing here is. I'll embiggen it for you. So if we took vector A plus B, so here's vector A, here's vector B, and then the resultant, which they have arbitrarily chosen S to represent, goes from the head of the first vector to the tail of the last one. There you go. Cool? All right. So what we learned last year was that doing this graphically is not super practical. At my old school, the teacher had students do it by making scale drawings, which was a giant hassle. But I don't know, he found value in it, and so, you know, whatever it is, what it is. So, but what we learned last year then was that you can add those vectors by looking at the components, right? Okay? And so in doing that, what you're really doing is you're saying, all right, well, this vector A has a positive Y component and a positive X component, right? Oops. My vector B has a positive X component and a negative Y component. It looks more or less that my Y components cancel out, right? More or less. And so my resultant would just be of magnitude AX plus BX, right? Assuming that my AY and BY truly cancel out. All right? So that's kind of the idea. All right? So, couple quick things about vector addition. It's commutative, which means you can add them up in any order. A plus B equals B plus A. Cool? Good. Maggie, did I skip through something too fast for you? You sure? Okay.
Okay, so when you drew out the thing and then you drew the triangles and it was like BY, BX.
Here, back here.
Yeah. So then, okay, no, I got it. Okay, so it would be AX plus BX. So adding those particular components to the X.
Yeah.
Is there an easier way to do that, or did you just?
That's sort of where we're headed. I'm trying to kind of plow through to like get to the example so you guys can actually see it in practice. All right. Everybody cool? Maggie, you sure you're good?
Yeah.
Everybody's happy? Okay. No, she's good. She's good. All right. So adding vectors, you can add them any order. It's associative, which means if you're adding three vectors, the order doesn't matter. So you can do A plus B and then add C. You can do A plus, whatever you get when you add B plus C, it doesn't matter. Again, there's nothing magic about displacement vectors. You know, we're going to work with velocity vectors and acceleration vectors and force vectors and momentum vectors, all treated equally, okay? Torque vectors when we get there.
Or?
Yep. Yeah, I know. Torque? What? It's a vector.
Oh, I thought
Yeah.
you said fork.
Torque vectors
I was like, what?
are they have different rules, but they're delicious rules. Okay. So read checkpoint 1. See if you can come up with an answer. The magnitudes of displacements of vectors A and B are 3 and 4 meters respectively. C is the sum of the two vectors. What's the biggest magnitude and the smallest magnitude you could get by adding those two vectors? Don't make it harder than it is. Okay, so let's take a second to run through this, you guys. So check it out. Vector A has a magnitude of 3, right? Whoa, that is not at all what I wanted to do. Oh well. Okay, so here's vector A. It's got a magnitude of 1, 2, 3. Good? All right, now, vector B, 1, 2, 3, 4. Oh, okay.
That's pretty.
Shut up! Okay, so here's my vector A, here's my vector B. I'm going to add them up graphically. All right? In order to get a maximum magnitude resultant, I want them to point in the same direction, right? When you add vectors, how do you place them? Head and tail. So, there we go. Maximum resultant is 7. Minimum resultant would be, we're just talking about magnitude, so I don't want to hear negatives, and that sounded snarkier than I meant to. But 1, right? Look. So there's vector B. Did I change it at all? I didn't change the magnitude. What did I do? Changed the direction. Okay, so now I'm going to do vector A plus B. So here's vector A plus B. Oh, I apparently should have measured it. What do I get? -1, right? And again, the negative just indicates direction. The magnitude is actually 1. Follow?
Why couldn't it be set?
Because the magnitude ignores the negative signs.
We just have -1.
Right, but the magnitude is 1.
It's like a car.
I don't know, but like, what if they both went in different directions? Oh, I got it.
So if they both went in a negative direction, you'd have a magnitude of 7,
Okay, but since
which is still 7.
because if you go this way or if you go that way, you have.
Right. Are we good or no? I feel like I'm not. Magnitude means ignore negatives.
Yep.
All right, are we good?
So is this just in meters, or we don't need the iron?
We're just talking magnitude, so that's not a vector. There'd be no I or j there. Okay, so is everybody good? All right. How about if I do this and add them? Oops, that's supposed to be pointing straight up. Then your magnitude would be 5, right? Because you'd have a 3, 4, 5 triangle, right? Which didn't fit on my screen, but you guys know what I'm trying to get at?
Yeah.
Cool? Everybody happy? All right, cool. All right, so, again, like I said, I kind of wanted to plow through this to get to an actual example where you can see how it works in practice. All right, which is this. All right, so we're basically going to be dealing with 2 different types of problems. Problems where you know the 2 vectors and you need to add them, or problems where you already know what you get when you add them, but you're missing one of the vectors to get you there. Okay, so here we go. Roy pushes a box with a force of 400 newtons at 60 degrees south of west. Sally pushes the same box with a force of 250 newtons at 30 degrees west of east. Find the net force. Honestly, I think I copied this from an old honors physics sheet. All right, so my suggestion is give these vectors names. Force of Roy is 400 newtons.
How do you go west?
Oh! That's embarrassing. West of north, sorry. Sorry about that.
Mr. Packer,
Yeah,
isn't west of east just straight west though? And you go half.
yeah, I guess so.
Yeah, because you,
All right. All right, so there's my first vector, force of Roy. Here's my second vector, force of Sally. All right, so what do you think your first step is? Draw a picture, all right? So let's do that. Let's see. So if you're struggling with the directions, it helps to start with drawing a compass. So here's my compass, north, south, east, west. So 60 degrees south of west is going to be this way, right? Now pause and think about where the 60 degrees is. Is it the top angle or the bottom angle?
It's top, because it's west.
South of west. So you start at west, and then you go south of it. So here's my 60 degrees. And draw in your components. So here's my force of Roy. Here's my force of Roy in the y direction. Here's my force of Roy in the x direction. And do the math. So, oops, this one was 400. So the x component is going to end up being negative 200 newtons. And the y component is going to end up being negative 360. Where did my calculator go? Here it is. 346, sorry. All right, I know, me too. All right. Problems with what I just did there? Everybody happy? Anybody confused? Confuzzled? Anything? We're all good? All right, so repeat the process for the force of Sally. I'm going to skip the drawing because you guys ought to know how to do this by now. Yes? Is that cool? So the force of Sally in the x direction ends up being, 30 degrees west of north. So here's north, west of it. So the x component is going to be 125, but negative. And the force of Sally in the y direction is 250 times 216.5, which we will just use 217. And it's positive, right? All right, everybody good?
So if you take the y components, between them and isn't that just
Isn't it what we're saying there?
no, it's y.
This one actually does happen to be 3069 triangle weirdly, but all right. So are we good? Everybody okay up to here? Okay. All right. So now what we're going to do? Remember, these are written in magnitude direction notation. So what we're going to do is we're going to rewrite them in unit vector notation. So this becomes negative 200I minus 346J newtons. Does that make sense? And again, this just gives us like a handy way of writing out our x and y components, right? Follow? All right, similarly, this bottom one is going to give me negative 125I plus 217J newtons. Cool? All right, and some of you are thinking, yes, this is a 30, 60, 90 triangle. There's a shortcut we could have taken here, and if you see that, cool. Although I don't know that that would have helped you find the direction, which this way will. Okay, everybody good so far? Cool. So, here's my net force. Everybody cool with the notation for net force? Is this what Hernandez used to do? What's the squiggly? Greek letter sigma, and in math it means sum. It means add these things up, right? So this is the sum of all the forces. All right, so literally, add up your x components, add up your y components. Okay, so we're going to get what? Negative 325 in the x direction, minus 125, 129, thank you.
What if they're different? What if it's like south and west?
Say that again?
What if it's like add south and west instead of to north?
No, those ends are newtons. Hey, Mr. McGuire, what's up? I don't know what big piece of paneling you might
Piece of ceiling paneling, we're gonna chop it up for whiteboards.
I don't think I ever got one.
Alright,
Oh, the whiteboards. No, I actually ordered real whiteboards.
okay.
And they are waiting to be installed.
I'm so steady.
No, you're okay. Oh, good. Do you need whiteboards? Is that what you're asking? Oh, a big thing. That I cannot help you with. All right. All right. Okay. On that note, let's continue adding our force vectors. Justin, you're not helping me any here. All right. He's laughing because he has the same third grade brain that I apparently do. All right. All right. All right. So. Okay, Justin.
That's like a 12-year-old boy kind of third grade.
Yeah, you're right. Okay.
Yeah.
All right. So, do we know where to go from here? So the idea is now we've got our vector and we know the components, right? Here's my x component, here's my y component, right? So my net force is going to have an x component of negative 325 newtons. Again, the n is newtons. And a y component. I'm mad that I wrote that there. Here, we're going to do this. Haha, take that. All right, and then a y component of negative 129. And we're looking for our net force, right? When do we get out? 09?
Yeah.
Yeah.
All right. Everybody good? All right. So, you can do, how do we find the magnitude of this guy? Pythagorean theorem, right? So, let's see, what are we going to get? Square root of 325 squared plus 129 squared gives you basically 350. And what else do I need to do?
Find the angle.
Find the angle. So I'm going to use the inverse tangent of 129 over 325. And it gives you 21.6 degrees. Am I done?
South of what?
South of west. We wouldn't have been able to get the 21.6 using Pythagorean theorem, and it won't always be a 30, 60, 90 triangle. So this will work for any set of angles. All right, are we good? Problems, questions, concerns, issues, anything? All right, you need to be familiar with being able to convert between magnitude, direction, and unit vector, and vice versa. Coolio? All right. Is that the end? All right. Oh, okay. So, shoot, we do not have time to do this. I think you do too. What if, let me see. All right, at the bottom of the next page, there's an example of vector subtraction. Oh shoot, but it's a little more involved. You know, we can muscle through tomorrow. That's fine. We're okay. All right. So Wednesday, retest tomorrow for notes. All right.